Alrighty, so we are like that going to continue on with section 7.3, trig substitutions. So we have two more examples for this chapter, trying to get through them. So I'm just going to jump right into the first one. So we want to evaluate the integral from 0 to 3 radical 3 over 2 of x cubed divided by 4x squared plus 9 to the 3 halves power dx. Okay, so let's just go ahead and go through this. So right now, you look at this and it doesn't exactly look like a trig substitution right now. So we're used to seeing like square roots for trig substitutions. Those are when they're really useful. Doesn't look like a u substitution, doesn't look like integration by parts. So let's try and rewrite this in a way that makes it look like something that a trig substitution will work on. Let me give myself a little more room there, so I'm not right on top of that other integral. So 0 to 3 radical 3 over 2 of x cubed divided by, first thing I'm going to do is I'm going to rewrite this 4x squared plus 9 to the 3 halves. So anything to the 1/2 power is a square root. So I can write this as the square root of 4x squared plus 9 cubed. So anything to the 3 halves power is just the square root cubed, really. Because you can write that however you want. You can write it as to the 3 times 1/2 or to the 1/2 times 3, and that'll turn it into that. Okay, but it still doesn't look exactly like we want it to. So I have the integral from 0 to 3 radical 3 over 2 x cubed. I'm going to pull a 4 out of the square root down there. So when I do that, I'm going to get a 2 because I have the square root of 4. And then an x squared plus 9 over 4 down there. This is all still cubed. So all I've done is factor out a 4 because 9 doesn't have a 4, it gets divided by 4. That's all that's happened there. So dx. And now things are starting to look a little better. They're starting to look like something that we can try as trig substitution on. So this is 0 to 3 radical 3 over 2 x cubed over 8. Just pulling the 2 out of the cube there. So x squared plus 9 over 4, sorry. Cubed. And now it looks like I can try a trig substitution. So this is, so I have an x squared plus 9/4, so that this looks like an x equals a tan theta. A squared in this case is 9/4, so a is the square root of 9/4, which is 3 halves. So I'm going to let x equal 3 halves tan theta. I'm not going to do the blue. I'll just box it off. So x is equal to 3 halves tan theta. Dx then is 3 halves root of tan theta is secant squared. We're on the d theta for the differential. And if I solve the first equation for for theta, I get theta is equal to the arctan of 2x over 3. We're going to need all that. The reason I need the theta part is I need to change my bounds of integration. So I'm going to change my bounds of integration. I'm going to plug in x equals 0 and x equals 3 radical 3 over 2 to change my integration bounds. So when x equals 0, I have the arctan of 0, which is 0. So tangent of 0 is 0, so the arctan of 0 is 0. The theta of 3 radical 3 over 2. So theta is the arctan of 2x over 3, so this is the arctan of 2/3 times 3 radical 3 over 2. And just keep simplifying, so this is the arctan. So 3's cancel and I get 2 radical 3 over 2. And let's pretend I don't have a calculator. I want to write this as, 2 values that appear for sine and cosine. This is the arctan of radical 3 over 2 over 1/2. And this ends up being pi thirds because the sine of pi thirds is radical 3 over 2. Cosine of pi thirds is 1/2. So the arctan of radical 3 over 2 over 1/2 is pi over 3. So that means this integral now, I can rewrite this as the integral from 0 to pi over 3. Box this off. This is scratch work. So x is 3/2 tan theta, so I'm going to get 3/2 tan theta cubed up top, divided by 8 square root of, so I have 3/2 tan theta squared, so 9/4 tan squared theta, plus 9/4. I want both those numbers to be the same because I'm going to end up factoring it out. This is all cubed. And then dx is 3/2 secant squared theta d theta. And now I'm just going to simplify. So I have everything I need plugged in. And now it's just a matter of simplifying this to get something that we can use. So 3/2 cubed is going to be 27 over 8 tan cubed divided by 8. I'm going to factor a 9/4 out of the radical. If I take the square root of that, that's 3/2. So I'm pulling it out of the radical. I have tan squared plus 1 cubed. And I still have this 3/2 secant squared theta d theta. And now it's just a matter of simplification. So I have the integral from 0 to pi over 3, 27 over 8. We'll do something with that in a second. Tan cubed, sorry, this should be tan cubed theta, tan squared theta, dropping the thetas, times 3/2 secant squared theta. Let's just pull that all into the numerator right there now that I have room. Downstairs I have 8. 3/2 to the third power is again 27 over 8. And then I have square root of tan squared plus 1. So tan squared plus 1 is secant squared. So this is then secant squared, or secant theta, because I'm taking the square root, cubed d theta. Yeah, so it's looking ugly, but you can see 27 over 8 cancels there. Now I'm left with, so I have 3/2 and an 8 on bottom. That's going to be a 3/16, which I'm going to pull out front in the integral. So I have 3/16 integral from 0 to pi over 3, and now I have a tan cubed theta secant squared theta divided by secant cubed theta theta. And let me just double check to make sure that is where we're supposed to be at right now. Yes. All right, so we can simplify some more. Haven't made any mistakes yet. 0 to pi over 3. I get, secant squared divided by secant cubed. I have a couple of those cancel. This is now tan theta divided by secant theta d theta. Okay, so we're going to keep going. Now we have to figure out how to integrate this, and this one is kind of a really obnoxious problem just because it's just a lot to do. You have to do a trig substitution. You have to figure out how to integrate this. It doesn't look like we can really do anything in terms of a u substitution right now. Integration by parts isn't going to be helpful. So let's try writing everything in terms of sine and cosine. So tan cubed is sine cubed divided by cosine cubed. And 1 over secant theta, that's just cosine theta d theta. We're going to keep going, 0 to pi over 3. Now I have sine cubed theta over cosine squared theta, because one of the cosines canceled out, d theta. And now this is something I can do. So I can do a u substitution. U is equal to cosine theta. That way du is negative sine theta d theta. And we can change the bounds on our integral if we want. We can do u of 0 and u of pi over 3. So cosine of 0 is 1. cosine of pi over 3. This is 1/2. So this is 3/16, the integral from 1 to 1/2 of so I skipped a step, sorry, hang on. So that is the right u substitution. Let me just do one more step here, 0 to pi over 3. I'm gonna write this as sine squared theta divided by cosine squared theta. And I need another sine theta because it was a sine cubed. And the reason I'm doing this is because I want to write everything I can in terms of cosine. That way this sine theta d theta is already taken care of in the u substitution. So everything else needs to be a cosine. So sine squared is 1 minus cosine squared theta over cosine squared theta, sine theta d theta. And now I do the u substitution. So I have 3/16, the integral from 0 to pi over 3, 1 minus u squared over u squared. Sine theta and d theta is minus 1 over sine theta du. So just doing the u substitution, so this is negative 3/16. Minus sign comes from the minus 1 over sine theta. Sorry, change the bounds on my integral now. So my integral, instead of going from 0 to pi over 3, now goes from 1 to 1/2. 1 minus u squared over u squared du. I'm going to let you guys fill in the steps here because I don't want this, because this is a really long problem. So this is, something that you can integrate now. Just break it up into 2 different parts. This will help you for your exams and things like that. But when you do this integral, you're going to get positive 3 over 32. And so I'm leaving that for you guys to work through. So yeah, so that'll take care of that. Okay, so just double checking my minus signs are right here. So everything seems okay. Yes. All right. Okay. So I'm going to move on from here then. So again, your job is to do this integral and get 3 over 32. It's pretty easy. You can do that directly by splitting the fraction up. Let's move on to this last example. It's a good example of, so this is a really good problem to know how to do. So we have the integral x over square root of 3 minus 2x minus x squared dx. So if you look at this, again, this doesn't fit the pattern of the trig substitutions we've been doing. So we're used to seeing, x squared plus a squared, x squared minus a squared. So the first thing I'm going to do is factor that minus sign out here, just because I want that x squared to be up front and center. And then we'll talk about what to do here. Okay, so like I said, this so this isn't, so if you're going to try to do a trig substitution on this, trying to think if, so I'm looking at this and seeing if you could do a u substitution. You might be able to, but it might be more difficult than the trig substitution. You might have to do 1 or 2 u substitutions. So I'm going to do this with a trig substitution. But the first thing I'm going to do is I want to, be able to write this as like x squared plus a squared, x squared minus a squared, something like that. And to that end, I'm going to complete the square in the bottom. So you should remember this, or at least be familiar with the phrase from your algebra classes. All completing the square is adding and subtracting. B over 2a squared. And that b over 2a is talking about with the polynomial down bottom, the quadratic x squared plus 2x minus 3. So in this case, you know, b is equal to 2, a is equal to 1. So b over 2a squared then is going to be 2 over 2 times 1 squared, which is 1 squared, which is 1. So the idea behind this is this x squared plus 2x minus 3. This is the same thing as x squared plus 2x plus 1 minus 1. So I've added and subtracted my b over 2a squared, and I still have this minus 3 at the end. So I haven't changed this at all, which is why I can still write equals. I've just added and subtracted 1. I've added 0 to this. And now what you'll notice is this first term is a perfect square. That means I can write it as x plus 1 all squared. That's what a perfect square is. And then minus 1 minus 3 is now minus 4. So my integral now becomes so let me actually use some of the tools I have here. I think I can actually grab this and copy it. Yeah, there's a way to do this. Nope, we're going to leave it alone. All right, so my integral then is, so it was x over the square root of negative x squared plus 2x minus 3. But after completing the square, this is now the integral x over square root of negative. Then I have x plus 1 squared minus 4 dx. So that comes from completing the square here. X plus 1 squared minus 4. And now what you can see is this almost looks like a trig substitution. This is the integral x over square root. I'm going to distribute that minus sign. Now this is 4 minus x plus 1 squared dx. Almost looks like a trig substitution here. So we're going to do a u substitution so that u is equal to x plus 1. And du is just dx. So when I do this u substitution, I'm going to have to replace this x up top. So I'm going to solve the u is equal to x plus 1 for x, and make it x is equal to u minus 1. So now when I do this, I'm going to have the integral x up top is now u minus 1 divided by the square root of 4 minus u squared du. And now this is something I can do a trig substitution on. I can do the first one in the chart there, u is equal to a sine theta. So a is going to be 2 in this case because 2 squared is 4. So I'm going to do u is equal to 2 sine theta. Du is going to be 2 cosine theta d theta. And I'll save solving for theta later. So this is going to be equal to the integral of u minus 1. Sorry. Erase that because we're doing this in terms of theta now. So u is 2 sine theta minus 1 over the square root of 4 minus 4 sine theta. 4 sine squared theta d theta. Okay, so just keep going. So this is the integral of 2, sorry, not, sorry. So that shouldn't just be d theta. It is 2 cosine theta d theta right here. So this is the integral 2 sine theta minus 1 over, pull the 4 out, the square root, you get 2 square root of 1 minus sine squared theta, 2 cosine theta d theta, and you can start seeing where this is going to go. It's starting to look a lot better. So this is 2 sine theta minus 1 over 2. 1 minus sine squared is cosine squared, square root. I get a cosine theta, 2 cosine theta d theta. So this one actually works out really nicely. That 2 cancels that cosine theta cancels. And I'm left with the integral of 2 sine theta minus 1 d theta. And this integral is doable. So we know how to do this one. This is 2 times, sorry, I'm doing the integral, I can drop it. So this is minus 2 cosine theta, because I've integrated sine theta, minus theta, plus your integration constant. And now we have to do all of that. You have to go back to your triangle there. So when you do that, so I'm going to leave that to you. So drawing the triangle, because this one's going on a little long, but I'll give you what you're supposed to get there. So when you draw the triangle, so you have theta is the arc sine of u over 2. So you can do this, so this is theta here, which is the arc sine of u over 2. I'm not going to fill that out. So opposite over hypotenuse, this would be u, this would be 2 then. And this would be the square root of 4 minus u squared. So you can figure out what the cosine of the arc sine of u over 2 is. So this can be minus 2 cosine of, so the cosine of that angle is going to be adjacent over hypotenuse. Square root of 4 minus u, drop the cosine. So cosine of theta, that would then be the square root of 4 minus u squared over 2 minus theta is the arc sine of u over 2 plus your constant. So that's scratch work over there. And now last thing to go back, we don't want it in terms of u, we want it in terms of x. U was, if you look up, x plus 1. So this is 4 minus x plus 1 over 2 minus the arc sine of x plus 1 over 2 plus a constant. Sorry, that's supposed to be u squared, so at 4 minus x plus 1 squared. And so you can write this as the square root of negative 4 minus x plus 1 squared. You can expand that quadratic if you want. I'm going to leave it. And this could be your answer. So we want everything in terms of x, so we have to go back and do that. So these problems can get kind of involved. This wouldn't be a very good quiz problem because it's so long. Might be a good exam problem, so you want to know how to do something like this. And I'm sure it's a homework problem somewhere. These are, good homework problems also. So I'm going to finish the video here. If you have any questions about this one, feel free to email me. I'm going to actually post these notes so you can watch them as I'm doing this, because these take a little longer and I go back and look at things. So I'm going to start posting these notes because they save anyway. So I'm going to stop the video here. So stop